Hello class, in this video, I'll be introducing concavity and inflection points. Let's begin. The concavity of the graph of a function refers to the behavior of its curves. When the graph is concave down, the tangent lines are above the graph, the value of the derivative is decreasing, and the curve creates a hill, in quotation marks. When the graph is concave up, the tangent lines are below the graph, the value of the derivative is increasing, and the curve creates a valley, in quotation marks. The diagram below shows what it looks like for a graph to be concave down or concave up. If you look at the interval to the left of the dotted line that I just drew, the graph is concave down. Since the graph is concave down, the derivative is decreasing, so the second derivative will be less than 0. If you look at the interval to the right of the dotted line, the graph is concave up. This means the value of the derivative is increasing, so the second derivative is positive. Now we have an interval where the second derivative is negative and an interval where the second derivative is positive. I drew the dotted line through what's called an inflection point. And at an inflection point, the second derivative is equal to 0. Now I'm going to introduce a test for concavity. Let f be a function where both the first and second derivative exist at all points in an open interval AB. Then, if the second derivative is less than 0, then the graph of f of x is concave down. If the second derivative is greater than 0, then the graph of f is concave up for all x in AB. Now on to the inflection points. An inflection point of a function f is a point in the domain of f where concavity changes. If x is equal to r is an inflection point of a function f, then the second derivative at r is equal to 0, or the second derivative at r is undefined. Now there are two main takeaways from this definition. The first is that r must be in the domain of f. The second is that the graph must change concavity at x is equal to r. If either of these are not true, then there is no inflection point at x is equal to r, even if the second derivative is equal to 0 at r, or the second derivative is undefined at r. So this leads to the following not always being true. If the second derivative at r is equal to 0, or the second derivative at r does not exist, then x is equal to r is the location of an inflection point. To demonstrate my point, I'm going to show you the function f of x is equal to x to the fourth. The second derivative is 12x squared. If we set the second derivative equal to 0, then x is equal to 0. Now my claim is that even though the second derivative at 0 is 0, there is no inflection point at x is equal to 0 because the graph does not change concavity at x is equal to 0. So I'm going to graph x to the fourth in Decimus and show you that x is equal to 0 is not an inflection point. So I've gone ahead and graphed the function into Decimus. And now all that's left to do is to evaluate the second derivative at 0. The second derivative when x is equal to 0 is 0. However, if you look at the origin, the graph does not change concavity at x is equal to 0. In fact, the graph of this function is always concave up. So what this means is that when you set the second derivative equal to 0, and you solve for x, you must make sure that the derivative changes signs at that value of x that you found. because if it does, you have an inflection point. If it does not, you do not have an inflection point. So now let's take a look at an example. For example 7, we want to find the inflection points, then determine the intervals where the graph of the function is concave up or concave down. Now before we start any of this, we need to determine the domain of m of x. Since this function is a polynomial, the domain is all real numbers. Now that we have the domain, we are ready to find the potential inflection points. To do this, we're going to need the second derivative. The derivative of m is negative 6x squared plus 18x plus 168. The second derivative is negative 12x plus 18. If I set the second derivative equal to 0, I can solve for x by subtracting 18 from both sides and dividing both sides by negative 12. So we have x is equal to 3 halves. 3 halves is in the domain of this function, so it can be a potential inflection point. However, we will not know until we determine if the sign of the second derivative changes signs at x is equal to 3 halves. So to do that, I'm going to create a number line. On this number line, I'm going to place the potential inflection point, and we know that the second derivative at 3 halves is equal to 0. So there are two intervals to test. The first interval is where x is less than 3 halves, and the second interval is where x is greater than 3 halves. I will start by testing the interval where x is less than 3 halves. If I choose x is equal to 1, the second derivative when x is equal to 1 is 6, which is greater than 0, which means the second derivative is positive when x is less than 3 halves. Now to test the interval where x is greater than 3 halves. If I let x equal 2, then the second derivative at x is equal to 2 is equal to negative 6, which is less than 0. This means that the second derivative is negative when x is greater than 3 halves. So we can conclude, since the derivative at x is equal to 3 halves is equal to 0, and the derivative changes signs at x is equal to 3 halves, there is an inflection point at x is equal to 3 halves. Now all we need to do is find the inflection point. To do that, we're going to substitute 3 halves back into the original function, and I'm going to do that in Desmus. So I've already gone ahead and entered the function into Desmus. So now I'm going to evaluate the function when x is equal to 3 halves. So there's an inflection point at 3 halves, comma, 525 halves. Now to determine where the graph of the function is concave up or concave down. The graph of the function is concave up in the open interval negative infinity to 3 halves. And that is because the second derivative is positive in that interval. The graph of the function is concave down in the open interval 3 halves to infinity, because that's where the second derivative is negative. And we are done.